All right, hello everyone. Welcome to the second part of the video for section 4.8. We're continuing forward with a couple more examples of how we can use L'Hopital's rule, some other indeterminate forms that might come up with problems of this type. Okay, so looking at this limit here, we have the limit as x goes to 0 of x times ln of x. And let's again look at trying to figure this out if we just use the techniques that we've already learned for evaluating limits. And first of all, we know here that in our limit, we have two functions being multiplied. When you have something like that, you can break your limit into the limit of the first function times the limit of the second. So we can make this the limit as x approaches 0 of x times the limit as x approaches 0 of ln of x. All right, and the limit as x approaches 0 of just x, well, there, 0 is in the domain of that function x, so we can just go ahead and plug that in and get 0. For the limit as x approaches 0 of ln of x, notice that 0 is not in the domain of ln of x. We can't plug in 0. So in this one, we can think about the graph of the function of ln. And you may remember that the graph of this function looks something like this. That's what the ln function looks like. And notice that here, as the input values are getting closer and closer to 0, they're only coming from one side, from the right-hand side. It looks like the output values are getting lower and lower, or smaller and smaller, so we're going towards negative infinity. So it looks like our limit comes out to be 0 times negative infinity, which you may think just immediately comes out to be 0. But unfortunately, because we have an infinity here, that's not how these things work. Okay, so this is actually an indeterminate form. Now, I'll tell you right now, we're going to work through this using L'Hopital, and the answer will actually come out to be 0. Okay, unfortunately, we can't just get it from this reasoning though, so I just want to clarify that to begin with. So here's what I'm going to do first, is I'm going to take this function x times ln of x. I'm going to rewrite it as ln of x over 1 over x. Now, are those two things the same? Are this here and this here the same? Well, let's double check if they are. So with this new form I've written, I have ln of x over 1 over x. So I have two things being divided, and the second one's a fraction. And remember, if you divide with fractions, you take the top thing, leave it as is, take the bottom thing and do the reciprocals. So instead of 1 over x, we can make it x over 1, and then we multiply those two things. And we do that in this case, notice that we do get x times ln of x. Okay, so those two things are, so what I have here in this green box and here up here, those are the same. So what I can do then is rewrite the limit as x approaches 0 of ln of x over 1 over x. And notice here I can't actually plug in 0 either. We get an indeterminate form in both cases because both the top and the bottom function, 0 is not in their domains. So we use L'Hopital, we'll take the derivative of both the top and the bottom. When we do that on the top, the derivative of ln of x is 1 over x. Derivative of 1 over x, recall we can rewrite that as x to the negative 1. If I take the derivative there, I'll get negative 1 times x to the negative 2, which I can rewrite as the limit as x goes to 0 of 1 over x over negative of 1 over x squared. And then again, we are now dividing with two fractions. So I have 1 over x on the top, negative 1 over x squared on the bottom. So if we rewrite that now, this will become the limit as x approaches 0 of the first thing, 1 over x, times now the reciprocal of the second thing, which would be negative x squared over 1. Here we can reduce some x's, so cancel out an x here with 1 up here. We end up with the limit as x approaches 0 of negative x, which now 0 is in the domain of this function, so we can just plug in 0 and we get 0 as our answer. Okay, so again there we used L'Hopital and some algebraic manipulation. All right, let's look at some other types of indeterminate forms we might get. So let's say that we have a limit where it's set up as the limit as the inputs approach some value of a function raised to another function, or raised to the power of another function. Well, you may recall from our limit rules, one way to deal with that is take the limit of the lower function and the upper function. And when we do that, let's say we get something like where the limit of the lower function is 0 and the limit of the upper function is 0, so we have 0 to the 0. Well, that's another one of our indeterminate forms that would indicate we may need to use L'Hopital. Similarly, if the lower function comes out, the limit there comes out to be plus or minus infinity, and the upper one comes out to be 0, then we'll have plus or minus infinity to the 0th, which is another indeterminate form. And if the lower function, that limit there ends up being 1, and the upper function ends up being plus or minus infinity, we get 1 to the plus or minus infinity. That's also one of our indeterminate forms. And again, when we see those, that often means that what we need to do to find the limit is use L'Hopital. Okay, so let's apply that to this function, or this limit here. So notice we have the limit as x goes to infinity of 1 plus 1 over x raised to the xth power. And we can think of this if we say that our lower function f of x is 1 plus 1 over x, and our upper function g of x is x, then what we really have here is the limit as x goes to infinity of f of x raised to g of x, right? And so let's take those two limits separately, the limit of the f of x and the limit of the g of x, and see what we get. So if we do that in green. So we do the limit as x goes to infinity of 1 plus 1 over x. We'll notice that doing that will give us in 1, and the reason for that is note that for this 1 over x here, as x goes to infinity, as the denominator there gets bigger and bigger, this part's just going to become 0. So we have 1 plus 0, so we just get 1. And then we'll take the limit of the upper function as x goes to infinity. It's the limit of x, and that's just going to be positive infinity. As the input values get bigger and bigger, the output values will also get bigger and bigger, which tells us here with our original limit that we end up with 1 to the infinity power, which as we saw was one of our indeterminate forms. So that indicates we need to use L'Hopital, but taking the derivative here will be really difficult because we have this x in the numerator, right? Or in the exponent, I mean. So how do we deal with that? Right, we're going to use some logarithmic stuff here. So what we're going to do is let y equal 1 plus 1 over x to the x. And then we're going to take the ln of both sides there. So we'll have ln of y will be equal to the ln of 1 plus 1 over x to the x. And notice that because we have the ln here on the right hand side and we have the ln of something raised to a power, we can use the product, or the we can use the properties of logarithms to move that out to the front. So now we have that ln of y equals x times ln of 1 plus 1 over x. okay? And believe it or not, this is going to be helpful for us to find our limit now. So here's what we're going to do. Clear all this. So we're going to kind of evaluate a different limit to start right now. So we're going to look at the limit as x goes to infinity of ln of y, that thing we were just looking at. But we just saw from how we chose what y was that this is the same as the limit as x goes to infinity. Ln of y was the same as x times ln of 1 plus 1 over x. And notice that this x times ln of 1 plus 1 over x has a similar form to the one we were just looking at. So we can rewrite this as limit of x goes to infinity of ln of 1 plus 1 over x over 1 over x. So just using that same trick we just used. And now we can use L'Hopital. We'll take the derivative of both the top and the bottom here. So we'll end up with the limit as x goes to infinity. We take the limit of the top here. We have an ln, so that means we're going to get 1 over what's there inside the ln times, we have to use the chain rule to multiply by the derivative of the inside here. We know the derivative of the constant is 0. Derivative of 1 over x, that's going to be negative 1 over x squared. We just saw that. Similarly, the bottom here, we have 1 over x, so take the derivative there. We'll end up with negative 1 over x squared. And notice what that has done for us is we have negative 1 over x squared on the top and negative 1 over x squared on the bottom. So we can cancel those. And this just becomes the limit as x goes to infinity of 1 over 1 plus 1 over x. Here now we see that the only thing that has an x in it is this 1 over x right here. And the limit of that as x goes to infinity is just 0. So we end up with 1 over 1 plus 0, which is just 1. Okay? So there we were able to incorporate a little bit of that logarithmic differentiation in with our L'Hopital. All right, that one, there's a lot of steps in that, so if you need to go back in the video and rewatch some stuff, I would suggest you do that. Otherwise, thanks for watching.